Good morning, I am Aditi studying in Bsc Chemistry Honors second year. Today in this video lecture we are going to read electromagnetic spectrum, absorption spectra, in other words ultraviolet spectroscopy. Introduction. One of the most important areas of interest of an organic chemist is to determine the structure of organic compounds, whether isolated from natural sources or prepared in the laboratory. The procedure generally employed consists of the following steps: purification, detection and estimation of elements, determination of molecular mass, calculation of the molecular formula, and determination of the structure. Till recently, the structure of organic compounds were mainly determined through their chemical reactions, degradations, and chemical syntheses. This process is quite tedious and time consuming. However, during the last 3 decades, a large number of physical methods have been developed which serve as powerful tools for the determination of structures of organic compounds. Of these, the most commonly used methods are the spectroscopy methods such as ultraviolet, UV, infrared, IR, nuclear magnetic resonance (NMR) spectroscopy, and mass spectroscopy. The molecular mass and molecular formula can be determined by the use of mass spectrometry. The nature of the functional groups present in an organic compound can be determined by a combination of UV and IR spectroscopies. The complete structure, including the stereochemistry of the organic compound, is then determined by the use of NMR spectroscopy. These spectroscopy methods of structure elucidation are preferred over the classical methods because of the following advantages. These requires only a small amount of the organic compound. These methods require a much smaller time and the information is obtained on a chart which serves as the permanent record. During most of the spectroscopy studies expect mass spectrometry, the compound remains unaffected chemically and hence can be recovered. Most of these methods are extremely sensitive to small changes in spatial orientation of the various atoms present in a molecule and hence are generally used to determine the stereochemistry of organic compounds. These methods are also useful for determining the mechanism and rates of chemical reactions. In this chapter, we shall discuss the basic principles and applications of some of the most commonly used spectroscopy methods in organic chemistry. Electromagnetic radiations. Visible light is a form of energy which can be described by two complementary theories: corpuscular particle theory and wave theory. Neither of these two theories can explain all the properties of light. Some properties of light, such as photochemical effect, black body radiations, can be explained only by corpuscular theory, while other properties of light such as diffraction, interference, etc. can be explained only by the wave theory. In this chapter, we are only concerned with the wave nature of light, which is briefly discussed below. Electromagnetic wave theory. Wave theory of light was put forward by James Clerk Maxwell in 1864. According to this theory, energy is emitted from any source such as heated rod or tungsten filament of an electric bulb continuously in form of waves or radiations, and the energy thus emitted is called the radiant energy. The most common example of radiant energy are heat, light, X-rays, gamma rays, etc. Each radiation consists of mutually perpendicular oscillating electric and magnetic fields, both of which are perpendicular to the direction of propagation of the radiation. In other words, radiations are associated with both electric and magnetic fields and hence are called electromagnetic radiations. All radiations have wave character and travel with the velocity of light. Some important characteristics of electromagnetic radiations. All radiations have the following characteristics. Wavelength: it is defined as the distance between two consecutive crests or troughs. It is generally represented by Greek letter and is expressed in number of units such as angstrom, micron, millimicron, and nanometer. Frequency: it is defined as the number of waves which pass through a given point in 1 second. It is represented by the Greek letter V and is expressed in terms of cycles, sec, or hertz, or simply as velocity. The linear distance which a wave travels in 1 second is called its velocity. It is represented by the letter C and is expressed in centimeters or meter. If c, lambda and v are the velocity, wavelength and frequency of any radiation, then wave number, it is defined as the number of waves present in 1 centimeter length, or simply as the reciprocal of the wavelength. It is usually represented by the symbol. Obviously, units of will be centimeter. Thus, if lambda is expressed in centimeter, is expressed in meters. Further sense. Electromagnetic spectrum. The field of spectroscopy deals with the study of absorption or emission of electromagnetic radiations. We are familiar with a number of different types of electromagnetic radiation, such as cosmic rays, gamma rays, X-rays, ultraviolet light, visible light, infrared rays, microwaves, radio waves, radar waves, etc. All these radiations travel with the same velocity but differ from one another in the wavelength or frequency of their waves. The arrangement of all types of electromagnetic radiations in the order of increasing wavelengths or decreasing frequencies is called the electromagnetic spectrum. The complete electromagnetic spectrum is shown in figure 11.1. You can see the figure. Complete electromagnetic spectrum will approximate ranges of wavelength of various radiations. Now the energy E of any radiation is related to its wavelength and frequency by the equation. What is spectroscopy? Spectroscopy may be defined as the interaction of matter with electromagnetic radiations so that energy is observed or emitted in accordance with the relation, where h is the Planck's constant and v is the frequency of the radiation and delta E is the energy difference between the initial and final states of the matter. Types of spectroscopies. The field of spectroscopy can be broadly divided into two categories: emission spectroscopy and absorption spectroscopy. Emission spectroscopy. When atoms or molecules are subjected to intense heat or an electric discharge, they observe energy and get excited. During this excitation, the electrons in the ground state of the atom or the molecule are excited to some higher energy state. Since the lifetimes of these excited states is short, so they return to some lower excited state or ground state and the absorbed energy is released as light. When the emitted radiation is passed through a prism, it gives rise to an emission spectrum. In case of atoms, such a spectrum recorded on a photographic plate commonly appears as bright lines upon a dark background, whereas molecules give rise to bands. Absorption spectroscopy. If electromagnetic radiation is allowed to pass through a transparent medium, some is reflected, some is absorbed, and the remainder transmitted. When transmitted light is passed through a prism or grating, an absorption spectrum is obtained. Figure 11.2. This spectrum indicates those portions of the incident lights that have been absorbed by the medium. You can see the figure 11.2 absorption and emission spectrum of sodium. For example, when sodium flame is examined by a spectroscope, it reveals the presence of two yellow lines called D1 and D2 corresponding to wavelength. And respectively, these two yellow lines constitute the emission spectrum of sodium. However, when the same sodium flame is placed in the path of an arc light, the spectroscope reveals the presence of all the spectral lines of white light except for the two lines corresponding to the wavelengths D1 and D2, which are now found missing, and two dark lines appear in their place. These two dark lines constitute the absorption spectrum of sodium. Whereas emission spectroscopy is useful for the study of atoms, absorption spectroscopy is generally used for the determination of structure of organic compounds. This is due to the reason that most of the organic compounds are not stable under the drastic conditions necessary to record an emission spectrum. Therefore, in this unit, we shall discuss only the absorption spectroscopy. Absorption spectroscopy. Depending upon the types of the electromagnetic radiation absorbed, the field of absorption spectroscopy can be divided into the following types: ultraviolet and visible, infrared, microwave, nuclear magnetic resonance, electron spin resonance spectroscopy. However, in this unit, we shall only study UV and IR spectroscopies. Units used in various absorption spectroscopies. The users of different spectroscopy techniques use different units of measurement of wavelength. In the ultraviolet and visible spectroscopy, the unit of measurement of wavelength is millimicrons or nanometers. In the infrared spectroscopy, the units of measurement are the microns or micrometers or wave numbers. Reciprocal wavelength of or number of waves per centimeter. In the nuclear magnetic resonance spectroscopy, the radio waves used are defined not in terms of wavelength but in terms of frequency or hertz. In the NMR region, the radio waves used have frequency in the megacycle per second region. Let us now discuss various aspects of UV spectroscopy in some detail. Ultraviolet and visible spectroscopy. The UV region of the electromagnetic spectrum extends from 100 to 400 nanometer, while the visible region extends from 400 to 800 nanometer. The UV region is further divided into spectral regions that expanding from 100 to 200 nanometer is called the far UV region, while that extending from 200 to 400 is called the near UV region. The subdivision is necessary for practical reasons. At or below 200, O2 observes strongly and 2 starts observing. Therefore, the region below 150 can be studied only by using evacuated instruments. This is why the region below 150 nm is called the vacuum region. Principle: whenever UV or visible radiation is passed through the solution of an organic compound, it is either absorbed or transmitted depending upon its wavelength and the molecular structure of the organic compound. As a result of absorption of energy, an electron gets excited from the ground's electronic state to some higher electronic state. During this absorption process, some of the molecules of the organic compound will collide with the photons of the radiant energy. Although a large number of such photon molecule collisions are possible, but only those will result in absorption of energy in which the energy of the photon exactly matches the difference in energies of the electron in the ground and the excited electronic states of the molecule as shown in figure 11.3. You can look at in the figure 11.3 absorption of an electromagnetic radiation. Thus much amount of energy is sufficient to bring about a chemical change. That is why photochemical reactions are usually carried out with UV or visible radiations. This absorption of energy in UV or visible region occurs due to the transitions between electronic energy levels within the molecule. That is why UV visible spectroscopy is called electronic spectroscopy. Laws of absorption. The absorption of radiant energy by molecules is governed by the following two laws: Beer's law, Lambert's law. Beer's law. It states that the amount of light absorbed is proportional to the concentration of the absorbing solute or to the number of the absorbing molecule present in a medium, and that each molecule absorbs the same fraction of incident light regardless of the concentration. Lambert's law. It states that the fraction of light absorbed by a homogeneous medium is independent of the intensity of the incident light, and that each successive unit layer of the medium observes of an equal fraction of the light incident upon it. Combining these two laws, the following empirical expression called Beer-Lambert law may be formulated as: look at the expression. I naught is equal to intensity of the incident light, I is equal to intensity of the transmitted light, C is equal to concentration of the solution in moles liter, so L is equal to path length of the sample, usually 1 centimeter, molar absorptivity or molar extinction coefficient. A stands for absorption, absorbance or optical density, OD, and usually has values between 0 to 2. Limitations. The Beer-Lambert law is rigorously obeyed when a single species gives the observed absorption. However, the law is not obeyed when different forms of the absorbing molecules are in equilibrium. For example, ketonal tautomers, solute and solvent from complexes through some sort of association. There is a thermal equilibrium between ground electronic state and a low-lying excited state. Fluorescent compounds or compounds changed by irradiation are present. Molar absorptivity. Molar absorptivity, formally known as molar extinction coefficient, is a property of the molecule undergoing an electronic transition. Its magnitude depends upon the probability of the transition and the size of the absorbing system chromophore. The typical values of molar absorptivity vary from 0 to 10 raised to 6. Values above 1C4 are termed high intensity absorptions, while values below 10 to 10 raised to 3 are called low intensity absorptions. Here the example regarding molar absorptivity. Instrument UV visible spectrometer. An instrument used to measure the percentage of radiation absorbed or emitted when radiation of certain intensity and wavelength ranges pass through the sample of an organic compound is called a spectrometer or spectrometer. Spectrophotometer or spectrometer. The modern ultraviolet visible spectrometer consists of a radiation light source, a monochromator, a detector, an amplifier, and some recording device as shown in figure 11.4. Look at the figure 11.4, a double beam UV vis spectrometer. The most suitable source of light in the UV region in the hydrogen or deuterium discharge lamp, while a tungsten filament lamp is used for the visible region. Most of the spectrometers are double beam instruments. The electromagnetic radiations from the light source are made to fall on a rotating quartz prism to get a quantum of wavelength, which are then separated into radiations of individual wavelength with the help of a number of quartz slits. The monochromatic light thus obtained is split into two beams, one of which passes through the sample dissolved in a transparent solvent and other through the solvent. The intensity of each emergent beam is measured with photocells, and then the instrument electronically subtracts the absorption due to the solvent from the absorption due to the sample. The resultant intensity signal is automatically recorded on a graph as a function of wavelength. This record of the percentage of the radiation observed or transmitted is called the absorption spectrum. Figure 11.6 and 11.7. Band nature of UV spectrum. A UV visible absorption spectrum consists of a few absorption bands rather than sharp peaks as explained below. Absorption in the UV and visible region occurs due to electronic transitions which require a large amount of energy, while lesser amount of energy is needed for vibrational transitions and still lesser for rotational transitions. Figure 11.5, electronic transitions giving rise to a band spectrum. In molecules, there are only a few electronic states. Each electronic state is associated with a number of closely spaced vibrational substates, and each vibrational state in turn has a series of closely spaced rotational levels. In principle, electronic excitations can occur from any vibrational sublevel of the ground electronic state, but these generally occur from the V0 level of the ground electronic state, figure 11.5. Because this is the most highly populated state of the molecules at room temperature. As a result of these transitions, the absorption spectrum of the molecule in the vapor phase would contain a large number of closely spaced lines which can only be separated with instruments of high resolution. However, if the UV spectra are scanned in solutions, this fine structure is generally not observed because of the solvent-solute interactions which tend to smooth out the spectrum into bands. Further, even in the vapor phase, the ordinary laboratory instruments cannot take distinction between these discrete lines and hence record broad absorption bands as a result of merging together of these absorption lines. Thus, UV and visible spectrum of organic molecules consist of bands rather than peaks. Presentation of spectral data. The ultraviolet visible spectrum is generally recorded as a plot of absorptions versus wavelength. It is customary to then replot the data with plotted on the ordinate and wavelength in nanometers or millimicrons or abscissa, since the values of molar extinction coefficient vary from. This is from more customary to plot log as ordinate against wavelength as abscissa. Look at in the figure 11.6. The UV or visible spectrum usually consists of one or more absorption bands. The position of each absorption band is indicated by is the wavelength corresponding to the top of the absorption band is the intensity of absorption at this point. For example, the UV spectrum of acetone in hexane in figure 11.6. This is the figure 11.6 and this is the figure 11.7, ultraviolet spectrum of benzoic acid in cyclohexane. However, if the molecular mass of the organic compound is not known, its or log cannot be calculated. In such cases, the intensity of absorption is expressed as absorbance of 1% solution of the compound in a cell of 1 cm path length. Sample handling. The UV or visible spectra are usually recorded in the vapor phase or in solution. For this purpose, a variety of quartz and silica cells of path lengths between 1 to 10 cm are available. Although cells with 1 cm square area are commonly used, and these require approx 3 ml of the solution. Glass cells cannot be used since glass observes strongly below 300 nm. The cells must be thoroughly cleaned either with a detergent or hot nitric acid before use. These must be properly stored and their optical surfaces should never be touched. Solvents and solutions. The UV or visible spectra are usually measured in dilute solutions. For this purpose, a few mg of organic compound are dissolved in a suitable solvent. A good solvent for recording the UV spectrum of any organic compound must fulfill the following criteria. It should be transparent in the wavelength range being examined. It should not absorb radiations in the same region as the substance whose spectrum is being determined. A large number of solvents are available for recording UV spectra. Some of these, along with their lowest cutoff points or lowest transparency limits, are given in table 11.1. Some common solvents for UV spectroscopy. Of the solvents listed in table 11.1, 95% ethanol and N-hexane are the most commonly used since each of them is transparent in the regions of the UV where interesting absorption bands from organic compounds are likely to occur. Absolute ethanol prepared azeotropic distillation of rectified spirit with benzene is not usually recommended since it contains traces of benzene which observes in this region. Non-polar solvents such as hexane and cyclohexane are usually used when the fine vibrational structure in the spectrum is desired. It should have no effect on the fine structure of an absorption band. For example, figure 11.8. Ultraviolet spectrum of phenol in ethanol and isobutane shows the UV spectrum of phenol in isooctane and ethanol in polar solvent, that is ethanol. The fine structure of the absorption band disappears due to H bonding between phenol and ethanol, but in non-polar solvents such as isooctane no such H bonding occurs and the fine structure of the absorption band is observed. It should not change the wavelength of absorption of any absorption band. For example, acetone shows an absorption band at 279 nanometer in hexane, while in ethanol it appears at 272 and in H2O at 264.5. From the above discussion, it follows that as possible, non-polar solvents such as hexane, isooctane, cyclohexane, etc. should be preferred over polar solvents such as acetonitrile, methanol, ethanol, chloroform, etc. Types of electronic transitions. The absorption of radiant energy by organic compounds in the UV and visible regions occur due to excitation of electrons from bonding or non-bonding molecular orbitals ground state to the anti-bonding molecular orbitals excited state, which are usually vacant in the ground state of the molecule. The various types of electrons which are present in a molecule are alpha, pi, sigma, pi and n non-bonding. The anti-bonding MO associated with sigma electrons with pi, while the n electrons are not associated with any anti-bonding MO since they are not involved in bond formation. Consequently, n electrons are present in atomic orbitals and hence have higher energy as compared to pi electrons. The electronic transitions that occur in UV and visible region are of the following types. These are shown in figure 11.9 along with their energies and shapes of orbital involved. Transition in which an electron is excited from sigma bonding MO anti-bonding MO are called sigma to sigma star transition. These transitions are shown by only those compounds in which all the electrons are involved in sigma bond formation. In saturated hydrocarbons, these require very high energy. Therefore, these transitions occur at short wavelengths or high frequency and are usually found in the vacuum or far ultraviolet region. For example, methane absorbs at 125 nm and propane at 135 nm. Cycloalkanes generally observe at a higher wavelength than their corresponding open chain isomers. For example, cyclopropane observes at 195 nm relative to propane which observes at 135 nm. This is due to the reason that because of angle strain, the ground state energy level of cyclic hydrocarbons is higher than the corresponding saturated analogues. and sigma star transitions. Transitions in which a non-bonding electron is excited to sigma star antibonding MO are called N sigma star transitions. These transitions occur in these compounds which contain heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. For example, alcohols, ethers, alkyl halides, amines, aldehydes, and ketones show this type of transition. These transitions require lower energy than sigma star transitions and hence occur at longer wavelengths than sigma and sigma star transitions. In fact, the energy required for these transitions depend upon the electronegativity of the heteroatom. Lower the electronegativity, higher the wavelength of absorption. For example, methyl chloride observes at, while methyl iodide observes at. This is due to the reason that chlorine has higher electronegativity than iodine and hence N electrons on chlorine atom are comparatively difficult to excite than an iodine atom. Similarly, amines observe at longer wavelength than alcohols because of lower electronegativity of nitrogen as compared to oxygen. For example, methyl alcohol absorbs at 195 nanometer and dimethylamine observes at 227 nanometer. The fact that the absorption at 227 in trimethylamine is actually due to N sigma star transition is proved by the observation that when its spectrum is scanned in aqueous acid solution, it does not show any absorption. This is due to the reason that in acid solution, the amine gets protonated. As a result, N electrons are not available since they are now involved in bond formation. Pi star transition in which a pi electron is excited to an anti-bonding pi star MO are called pi star transitions. This type of transition occurs in unsaturated compounds containing double and triple bonds and also an aromatic compound. These transitions generally require a large amount of energy and hence occur at wavelength. For simple organic compounds containing isolated unsaturated centers, the absorption due to pi star transition occurs well outside the range of ordinary spectrophotometers, but the intensity of these transitions is usually very high. For example, in saturated aldehydes and ketones, the pi star transition produces an absorption band of high intensity at about 185 nanometers. Similarly, unconjugated alkenes such as ethylene absorbs at 175 nanometer and simple alkynes such as acetylene observe around 170 nm. It may be mentioned here that the position of pi star transition is sensitive to substitution on the doubly bonded carbon atoms. In general, the presence of one alkyl group on the double bond produces a bathochromic shift of 5 nm. A bathochromic or red shift, as is called, means a shift to lower frequency and longer wavelength. And pi star transition in which an electron is excited from the non-bonding atomic orbital to the pi star MO are called N pi star transition. The orbital picture of N pi star transition is however shown in figure 11.10. Look at in the figure 11.10 N pi star excitation of carbonyl group. All organic compounds containing a double bond between carbon and some heteroatoms such as C double bond O, C double bond S, N double bond O, etc. show this type of transition. All the above transition along with their relative energies and the compounds in which they occur are summarized below. Pi star in alkenes and cycloalkanes, sigma pi star in carbonyl compounds, and sigma star in oxygen, nitrogen, sulfur, and halogen compounds. Pi star in alkenes, carbonyl compounds, alkynes, azo compounds, and pi star in carbonyl compounds. Or out of all these transitions discussed above, N pi star requires the minimum amount of energy and hence occurs at longest wavelength, well within the range of ordinary spectrophotometers. However, the intensity of absorption of these N pi star transition is very low. For example, the carbonyl group of saturated aldehydes and ketones shows a weak absorption due to N pi star transition around 280 to 290 nm. The low intensity of this band will be explained in the next section. Selection rule. Certain electronic transitions which at first sight appear to be possible are generally not observed. This is because certain restriction called selection rules govern these electronic transitions. These are listed below. Transitions which involve a change in the spin quantum number of an electron during the transition state do not occur. In other words, direct single triplet transitions are forbidden. Transitions between orbitals of different symmetry usually do not occur. For example, n-pi star transition is a symmetry forbidden. All such transitions which do not follow selection rules are called forbidden transitions. Transition probability. The magnitude of the molar extinction coefficient is the measure of the probability of a particular electron transition. Depending upon the value of transitions are of two types: allowed transitions, forbidden transitions. Allowed transitions. Transitions having between 10 raised to power 4 to 5 are called allowed transitions. These are generally due to pi star transitions. For example, the pi star transitions in 1,3-butadiene shows a strong absorption at 217 nm. Forbidden transitions. Transitions having between 10 to 1000 are called forbidden transitions. For example, n-pi star transition of saturated aldehydes and ketones shows a weak absorption between 280 to 290 nm. The value of the E mix among molar extinction coefficient among other things depends upon the geometries and symmetries of the orbitals involved in the transition. Pi star transition, both pi and pi star orbitals lie in the same plane, and hence the overlap between these orbitals in the excited state is quite large. As a result, pi star transitions are highly probable. On the other hand, n-pi star transition are symmetry forbidden. Symmetry forbidden does not mean that it never occurs, but implies only that its probability is very low. The low probability of the n-pi star transition is due to the fact that n electrons on the heteroatom are in a plane perpendicular to the pi star MO. Since the regions in space of these two orbitals overlap only poorly, the probability of excitation of the n electron to the pi star orbital is quite low. Nevertheless, n pi star transition does occur. This is due to twisting of the molecule in the excited state, which increases the overlap. Thus, although the n pi star transition is symmetry forbidden, but the vibrational interaction makes the transition partially allowed. Solvent effects. The polarity of the solvent usually shifts the position of an absorption band either towards longer wavelength or towards shorter wavelength, depending upon the type of electronic transition involved, as discussed below. N pi star and N sigma star transitions. If a group is more polar in the ground state than in the excited state, the N electrons in the ground state are stabilized relative to the excited state due to hydrogen bonding or dipole-dipole interactions with the polar solvent. As a result, the energy difference between the excited state and the ground state increases, and hence the absorption shifts towards shorter wavelength, as shown in figure 11.11. Look at the figure 11.11. Effect of polarity of solvent on N pi star and pi star transition. A carbonyl group is more polar in the ground state than in the excited state. H bonding or dipole-dipole interactions will lower the energy of the ground state more than that of the excited state, and hence the absorption shifts to shorter wavelength. For example, the absorption maxima of acetone, which appears at 279 nm in hexane non-polar, shifts to shorter wavelength as the polarity of the solvent increases. This shift of the absorption maxima towards shorter wavelength is due to H bonding evidently greater. The magnitude of this shift stronger is the H bond. In other words, the extent of H bonding decreases in the order water, methanol, ethanol, chloroform. The energy associated with absorption in water at 264.5 is approx, and in hexane at 279 nm corresponds to an energy change of, and hence may be regarded as, the strength of the H bond. Similarly, the polarity of the solvent shifts the N sigma star transition towards shorter wavelength. Pi star transitions. If a group is more polar in the excited state than in the ground state, the H bonding and dipole-dipole interactions with the solvent will stabilize the excited state more than the ground state. As a result, the energy gap between the ground and the excited state decreases, and the absorption shifts toward longer wavelength. Consider, for example, ethylene molecule. In the ground state, the pi electrons are almost equally distributed between the two carbon atoms, and hence the molecule is non-polar. But in the excited state, one of these carbon atoms becomes electron deficient and the other electron rich. As a result, the molecule is more polar in the excited state. Consequently, in polar solvents, pi star orbitals will be stabilized relative to pi orbital, and hence the absorption shifts to longer wavelengths. Simple chromophoric groups. The term chromophore was originally applied to a system which impacts color to a compound, Greek chromophorus, color carrier. For example, nitro group is a chromophore since it imparts yellow color to a compound. Similarly, aryl conjugated azo group is a chromophore since it imparts color to the azo dyes. But now the term chromophore is used in a much broader sense. Thus, a chromophore is now defined as any functional group that absorbs electromagnetic radiations irrespective of the fact whether it imparts color to the compound or not. For example, a carbonyl group is a chromophore since it absorbs in the UV region at around 279 nm with a molar extinction coefficient of about 15. Some of the important simple organic chromophoric groups along with their approximate are given in table 11.2. Some simple organic chromophore, look at in the table. From table 11.2, it is evident that chromophores are of two types. Chromophores such as C double bond C and single bond triple bond C, which contains pi electrons and hence undergo pi-pi transition. Chromophores such as single bond C double bond O etc., which contains both pi and n electrons and hence undergo pi-pi star and pi transition. Further, if a number of organic compounds have the same functional group or chromophoric group, all these compounds will generally observe at very nearly the same wavelength and they will very nearly the same molar extinction coefficient. Therefore, it is impossible to determine the functional groups present in a molecule by comparing the UV spectrum with the data given in the literature for known compounds. Exochromes, groups which themselves do not show any characteristic absorption above 200 nm but which, when attached to a given chromophore, usually cause a shift of the absorption band to longer wavelength with a simultaneous increase in the intensity of the absorption band are called exochromes. Some common examples of exochromic groups are OH hydroxyl, NH2 amino acid sulfyl hydryl and their derivatives such as OR, NHR, NR2, SR, etc. And some of the halogens. For illustration, consider the following examples. First, trans-azobenzene absorbs at 320 nm. However, the presence of an exochrome such as ethoxy group at the p position shifts the nm with twice the intensity. Because shows an absorption band and 254 nm with 204, but aniline shows at 200 nm. Thus, NH2 groups act as an exochrome. However, the anilinium ion, which does not contain non-bonding electron, shows, which is characteristic of the benzene ring. Mechanism of action. One of the characteristic features of all the exochromes is that they contain non-bonding electrons. These non-bonding electrons extend the conjugation of the chromophore by sharing of the non-bonding electrons as shown below. In other words, the shift towards longer wavelength bathochromic effect produced by exochromes is due to extended conjugation. It will be discussed in the next section that the effect of extended conjugation is to reduce the energy difference between the ground and the excited state. As a result, the absorption shifts to longer wavelength with simultaneous increase in the intensity of the absorption band. Changes in position and intensity of absorption bands. For isolated chromophores such as the absorption occurs below 220, a region which cannot be studied with the commercially available spectrophotometers. However, the position of maximum absorption and its intensity can be modified by substitution of certain groups in place of hydrogen on the basic chromophore structure. These subsequent groups can produce the following four kinds of effects on the absorption. Bathochromic shift or the red shift. Shift no longer wavelengths or lower frequencies. Hypsochromic shift or the blue shift. Shift to lower wavelength or higher frequencies. Hyperchromic effect, an increase in intensity. Hypochromic effect, a decrease in intensity. Bathochromic shift or red shift. The shift of absorption maxima to longer wavelength is called bathochromic shift or the red shift. This can be achieved by the following three ways: by attaching an exochrome to the carbon-carbon double bond or the benzene ring as discussed above. Placement of an exochrome such as ethoxy group at p position of trans-azobenzene shifts its longest wavelength absorption band by 65 to longer wavelength and also increases its intensity twofold, that is trans-p ethoxybenzene. Similarly, substituent of H atom of benzene by an exochrome such as NH2 group shifts its primary absorption band from 203.5 nm to 230 and secondary absorption bands from 254 nm to 280 nm. Table 11.3. The reason for this bathochromic shift is due to the interaction of the n electrons of the exochrome with the pi electrons of the benzene ring chromophore, thereby stabilizing the excited state. As a result, the energy gap between the excited state and the ground state decreases and the absorption shifts to longer wavelength. Furthermore, the availability of n electrons greater is the bathochromic shift, since O is more electronegative than n. Therefore, the lone pair of electrons on n are more easily available for interaction with pi electrons of the benzene ring than those on the O atom. As a result, bathochromic shift is expected to be larger in aniline than in phenol. For example, in going from benzene to phenol 11.3 table, the primary band shift from 203.5 to 210.5, while the secondary band shifts from 254 to 270 nm. In contrast, in going from benzene to aniline, the primary band shifts from 203 to 230 nm and the secondary band shifts from 254 to 280. Further, since the n electrons of phenoxide ion as compared to phenol are expected to be more easily available for interaction with the aromatic pi system, therefore the bathochromic shift in both primary and secondary bands of phenoxide ion are expected to be larger than those in phenol. For example, in going from benzene to phenoxide ion, table 11.3, the primary band shifts from 203 nm to 235 nm, while the secondary band shifts from 254 to 287 nm. Unlike ethoxy and amino groups, which exert like bathochromic effect through interaction of their n electrons with the electrons of the pi system, alkyl groups exert their bathochromic effect through hyperconjugation effect. Since hyperconjugation is a much weaker effect than pi conjugation, therefore bathochromic shift produced by alkyl groups are often small. For example, ethylene absorbs at 175 as compared to 1-butene, which observe at 185, and isobutylene to methylpropene observe at 188. Here the bathochromic effect increases as the number of alkyl group increases. By conjugation of two chromophores, for example, ethylene absorbs strongly at 175 nm in the far UV region, but when the two double bonds are brought in conjugation, just as in butadiene, the pi star transition undergoes a bathochromic shift with hyperchromic effect, and butadiene observes at 217 nm. By decreasing the polarity of the solvent, for example, acetone shows Nm in H2O due to n-pi excitation. If hexane is used as a solvent, the absorption maximum shifts to 279 nm. Hypsochromic shift. A shift of absorption maxima to shorter wavelength is called hypsochromic shift or the blue shift. This may be caused by the following two factors. By attacking an exochrome to the C double bond O group, for example, n-pi star transition of acetaldehyde appears at 293 nm, but it undergoes a hypsochromic shift when its H atom is substituted by an oxochrome as shown below. The hypsochromic shift of the n-pi star transition is primarily due to I effect of the heteroatom ON or Cl. These heteroatoms withdraw electrons from the carbonyl carbon, causing the lone pair of electrons on the carbonyl oxygen atom to be held more firmly than they would be in the absence of the inductive effect. As a result, the energy of the n orbital decreases more than that of the pi star orbital. In other words, energy gap between n and pi star orbitals increases, and hence the absorption shifts towards shorter wavelength. By increasing the polarity of the solvent, for example, n-pi star transition of acetone in hexane appears at 279, but this absorption shifts to lower wavelength and appears at 264 in water. As already explained, in this blue shift is due to H bonding, which lowers the energy of the n electrons, thereby increasing the energy gap between the n and pi star orbitals. Hyperchromic effect. This effect leads to an increase in molar absorptivity. Further, bathochromic effect is often accompanied by hyperchromic effect. For example, when phenol is converted into phenoxide ion, both the primary and secondary bands of phenol show a chromic shift with hyperchromic effect as shown in table 11.3. Hypochromic effect. This effect leads to a decrease in molar absorptivity. Further hypochromic shift are often accompanied by hypochromic effect. For example, when benzoic acid is converted into benzoate ion or aniline is converted into anilinium ion, both the primary and secondary bands exhibit hypochromic shift with hypochromic effect as shown in table 11.3. Effect of conjugation. If an organic molecule contains two or more chromophores which are separated by two or more single bonds, their effect on the spectrum is usually additive. This is due to the reason that there is little electronic interaction between these isolated chromophoric groups. However, when the two chromophoric groups are conjugated or separated by one single bond, a large effect on the spectrum is provided since the pi electron system is now spread over at least 4 atomic centers as a result. The high intensity pi star transition absorption band is generally shifted by 1545 to the longer wavelength with simultaneously increase in intensity of the absorption band as compared to the unconjugated chromophore. Similarly, when a carbonyl group is brought in conjugation when a double bond, both the pi star and n pi star absorption bands are shifted to longer wavelengths. Some conjugated chromophoric groups are given in table 11.4. 11.4 Characteristics of some common conjugated chromophoric groups. From table 11.4, it is clear that conjugation of two chromophore not only produces a bathochromic shift but also increases the intensity of the absorption bands. Let us now discuss the effect of conjugation on the absorption spectra of dienes and polyenes and alpha beta unsaturated carbonyl compounds. Conjugated dienes. First, acyclic dienes. Simple alkenes such as ethylene observes at 175, but when two double bonds are brought into conjugation as in 1,3-butadiene, the pi star absorption band shifts to 217 with a simultaneous increase in the 20,000. This may be explained as follows. A double bond consists of two pi MOs, one bonding and the other anti-bonding, but when two double bonds are brought into conjugation, 4 MOs are formed. Two of these, pi 1 and pi 2, are bonding and are occupied by a pair of electrons each, while the other two are anti-bonding, pi star 3 and pi star 4, as shown in figure 11.13. Thus, it is clear that the energy of highest occupied molecular orbital increases while that of the lowest occupied molecular orbital decreases. As a result, the energy level involved in pi star transition now come closer and hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 star orbitals in 1,3-butadiene is much lower than the corresponding energy gap in pi and pi star orbitals in ethylene, and hence 1,3-butadiene observes at a longer wavelength than ethylene. Further, since the energy levels come closer, their interaction in the excited state increases and hence also goes up. Figure 11.19. In a similar way, we can show that when three double bonds are brought into conjugation, the energy gap between the HOMO and LUMO becomes still smaller, as shown by arrows in figure 11.14, and the pi and pi star absorption band shows a further bathochromic shift with a further increase in the absorption band. For example, 1,3,5-hexatriene show a strong pi and pi star transition absorption band. In general, greater the number of conjugated double bonds, greater is the bathochromic shift, so much that in some cases the absorption may even shift to the visible region. For example, trans beta carotene and orange pigment of carrots containing 11 double bonds shows two absorption bands. Cyclic dienes. Cyclic dienes are of two types: homoannular dienes, heteroannular dienes. Homoannular dienes, conjugated dienes in which the two double bonds are present in the same ring, are called homoannular dienes. Due to rigidity of the ring system, these dienes necessarily exist in the S-cis-soid orientation. Heteroannular dienes. Conjugated dienes in which the two double bonds are present in different rings are called heteroannular dienes. Due to rigidity of the ring system, these dienes necessarily exist in the S-trans-transoid orientation. For some reasons as discussed under acyclic dynes, homoannular or dynes absorb at longer wavelength but with lesser intensity as compared to heteroannular dynes which observe at shorter wavelengths but with higher intensity. For example, effect of endocyclic and exocyclic double bonds on the absorption maxima of dynes. A double bond is said to be exocyclic if it lies within a particular ring and exocyclic if it lies outside a particular ring. Consider for example the following compound. Look at this. Compound 1 contains two double bonds, both of which lie within rings and hence are called endocyclic double bonds. Compound 2 also contains two double bonds. The double bond between C1 and C2 lies within the ring and is called the endocyclic double bond, whereas the double bond between C3 C7 lies outside the ring and is called the exocyclic double bond. It is interesting to note that the same double bond can be exocyclic to one ring and endocyclic to the other. For example, consider compound ring A contains one double bond between C3 C4 and is thus endocyclic. Ring B contains two double bonds between C5 C6 and C7 C8. Both of these are endocyclic to ring B. At the same time, C5 C6 double bond is exocyclic to ring A and C7 C8 double bond is exocyclic to ring. Similarly, ring C contains one double bond between C9 to C11 which is endocyclic to ring C but exocyclic to ring B. In general, each exocyclic double bond increases the wavelength of absorption of a given cyclic conjugated diene or polyene by 5 nm. The reason for this small bathochromic shift is that an exocyclic double bond distorts the stainless staggered conformation of the chair form of cyclohexane more than does an endocyclic double bond. As a result, the energy of the HOMO is raised. In other words, the energy gap between HOMO and LUMO decreases, thereby shifting the absorption towards longer wavelength. Woodward-Fisher rules for calculation of simple conjugated dienes. Woodward formulated certain empirical rules for calculating for the long wavelength pi star transition for dienes and polyenes. These rules were later modified by Fisher in 1959. According to these rules, each diene has a certain fixed basic value and the value of depending upon the following points: the number of alkyl substituents or ring residue present on the diene system, the number of double bond extending conjugation beyond on the diene system, the presence of polar groups or exochromes such as X, Cl, Br, etc., OR, Sr, NH2, O, CO, CH3, etc. The application of the above rules are illustrated by the following examples. Here are the examples. Linearly conjugated and cross-conjugated polyenes. If all the double bonds of conjugated polyene lie along a single continuous path, the polyene is said to be linearly conjugated, and if on the other hand all the double bonds do not lie on a single continuous path but contain a branched conjugated system, the polyene is said to be cross-conjugated. Consider for example polyenes. Whereas tetraene is linearly conjugated since all the four double bonds lie along a single continuous path. On the other hand, triene is cross-conjugated since all the three double bonds do not lie along a single continuous path. Such a system can often be resolved into two or more partial linear conjugated systems, and for the purpose of calculating the empirical rule suggested that the calculation be made on that partial linear system which absorbs at the longest wavelength. Thus, for the linearly conjugated tetraene, the rules predict, which is in excellent agreement with the observed value of 355. In contrast, triene is cross-conjugated. It can be resolved into two linear conjugated diene, heteronuclear annular diene with one double bond each in ring B and C, and the other homoannular diene in which the two double bonds are present in ring C. Since a homoannular diene absorbs at a longer wavelength than a heteroannular diene, therefore calculating the lambda max of triene homoannular diene system is considered as the parent diene, and the double bond in ring B is neglected. According the calculated value is 288, which is excellent agreement with the observed value of 285 nm. UV spectra of unsaturated ketones, enones. The UV spectra of unsaturated carbonyl compounds in which the double bond and the carbonyl group are not conjugated are simple summations of the absorption of the ethylene and carbonyl chromophores. In ethylene, the absorption occurs in the far ultraviolet region and is due to pi star transition, which being symmetry allowed in quite intense. The simple isolated carbonyl group gives rise to two bands as shown in figure 11.15. The short wavelength pi star transition band is quite intense, symmetry allowed, but it lies in the far ultraviolet region, much below the usual cutoff limits of the solvents, and hence is generally not observed. The second long wavelength pi star transition band is weak, symmetry forbidden, but is usually observed since it lies much above 280 nm, the usual cut-off limits of the solvents. Look at in the figure 11.15. However, when the C double bond C and C double bond chromophores are conjugated, both N pi star and pi star transitions are shifted towards longer wavelength through chromic shade. For example, mesitile oxide and alpha beta unsaturated ketone due to transition and hexane due to transition, whereas ethylene shows NM transition and acetone shows NM due to N pi star transition. The energy level diagram of an alpha beta unsaturated carbonyl group is shown in figure 11.16. This diagram is however more or less similar to that of butadiene as shown in figure. It is evident from figure that the energy of the HOMO of alpha beta unsaturated carbonyl compound is higher than the pi orbital of the ethylene or the carbonyl chromophore. Similarly, the energy of the LUMO of the alpha beta unsaturated carbonyl compound is lower than the energy of the pi star orbital of the ethylene or the carbonyl chromophore. Hence, the pi star transition of the alpha beta unsaturated compound is shifted towards longer wavelengths. Is pi 3 star is lower than pi star of the isolated carbonyl. The promotion of one of the oxygen lone pair electrons N to pi star requires less energy than the similar promotion in the isolated carbonyl group, and hence the N pi star transition is also shifted towards longer wavelength. Woodworth-Fisher rules for calculation of for pi star transition absorption band of alpha beta unsaturated carbonyl compounds in enones. We have discussed above that when a double bond is conjugated with a carbonyl group, it gives two absorption bands, an intense absorption band in the region 220 to 250 nm due to pi star transition, and a weak absorption in the region 310 to 330 nm due to N pi transition, while the pi star transition is affected in a predictable manner by structural modification of the chromophore. N pi star transition does not show this predictable behavior. Woodward and Fisher examined the UV spectra of a number of alpha beta unsaturated compounds in ethanol and formulated a set of empirical rules which help us to predict the lambda max of pi star transition in an unknown compound. These rules are summarized. Solvent correction. Since pi star absorption band is strongly affected by polarity of the solvent, therefore, to convert lambda max values obtained in other solvents to standard ethanol solvent, the following solvent corrections have been proposed. Rules for calculating pi star transition absorption band of alpha beta unsaturated carbonyl compounds. Base values: alpha beta unsaturated acyclic or 6-membered ring ketone 215, alpha beta unsaturated 5-membered ring ketone 202, alpha beta unsaturated aldehydes 202, 7 alpha beta unsaturated acids or esters 197. Instruments: each alkyl group or ring residue alpha beta 10 12, lambda gamma 18, each double bond extending conjugation 30, each exocyclic double bond 5, homoannular diene component 39, two double bonds which are conjugated with C double bond group lie in the same ring. These rules are illustrated by the following examples. Look at these following examples. linearly and cross-conjugated anones. If the two or more double bonds lie only on one side of the 2-keto group, if it is said to be a linearly conjugated enone, and if on the other hand one or more double bonds lie on either side of the keto group, it is said to be a cross-conjugated enone. For example, structure represents a linearly conjugated dienone, while structure represents a cross-conjugated dienone. Thus, a cross-conjugated dienone contains a branch chromophore. Such systems contain two overlapping alpha beta unsaturated ketone chromophores, each one of which will give its own pi star absorption band with a high extinction coefficient, but due to band nature of the spectra, only that alpha beta unsaturated ketonic chromophore which absorbs at longer wavelength with higher intensity is usually observed. In other words, in cross conjugation system, the longest wavelength absorption band is due to the most highly substituted simply conjugated system present. For example, consider the stereoideal anones. Dienone may be regarded to consist of two alpha beta unsaturated chromophores A and B as shown by dotted lines, whereas dienone A has only one beta substituent, dienone B has two beta substituents in addition to an exocyclic double bond. Therefore, chromophore is expected to absorb at a longer wavelength, and hence for the purpose of calculating we consider the most highly conjugated system B. Here are some problems for practice questions. Applications of UV spectroscopy. Some important applications of UV spectroscopy are discussed below. Detection of functional groups. UV spectroscopy has been used to detect the presence or the absence of certain functional groups in organic molecules. For example, if an organic compound does not show above 200 nm, it cannot contain a conjugated chromophore, an aldehyde or a keto group, a benzene ring or Br or I atom. However, it may possesses F or Cl, an isolated double or a triple bond, an amino, hydroxyl, carboxyl, ester, amido, cyano or mercapto group. Distinction between conjugated and non-conjugated compounds. UV spectroscopy can be used to distinguish between conjugated and non-conjugated compounds. For example, due to conjugation, both pi and pi star and n pi star absorption bands in compounds I will observe at a longer wavelength than those in compound. Similarly, completely conjugated and cross-conjugated dienones can be easily distinguished. For example, the cross-conjugated dienone observe at, while the completely conjugated dienone observe at 278 and hence can be easily distinguished from each other. Determination of extent of conjugation. One of the most important uses of UV spectroscopy is to detect and estimate the extent of conjugation in conjugated polyene. Butadiene itself observed at 217 nm, but addition of each double bond shifts the absorption maxima to the longer wavelength by about 30. Greater the number of such conjugated double bonds, longer is the wavelength of absorption. So much so for compounds containing 8 or more conjugated double bonds, the absorption in fact occurs in the visible region and the compound appears colored to the human eye. For example, trans beta carotene, a orange color pigment of carrots which contains 11 conjugated double bonds, show two absorption maxima at 452 nm and 478 nm. Similarly, lycopene, a compound partly responsible for the red color of tomatoes, also has 11 conjugated double bonds and hence observed at 505. Thus, by measuring the lambda max of an unknown polyene, we can determine the number of conjugated double bonds it actually contains. Detection of impurities. Compounds with large lambda max values can be detected when present as impurities even at low concentration, provided the sample itself does not show any absorption in the region of impurities. A practical application is the detection of benzene present as an impurity even at low concentration in a sample of ethanol. As stated earlier, in this type, absolute or anhydrous ethanol can be prepared from commercial ethanol or rectified spirit by azeotropic distillation with benzene ring Dean star apparatus. Because of toxic nature of benzene, it is desirable that ethanol meant for internal use must be free from benzene. Thus, traces of benzene, if present as an impurity in ethanol, can be detected by scanning its UV spectrum. If the UV spectrum of the sample shows an absorption 254, it contains benzene, otherwise not, because ethanol is transparent at this wavelength. Quantitative analysis. Due to this high sensitivity, UV spectroscopy is a valuable analytical tool. It is based upon Beer-Lambert law, which relates absorption A of the substance at a particular wavelength to its concentration C and molar absorptivity coefficient. A simple example of quantitative analysis of UV spectroscopy is the estimation of a mixture of anthrax and naphthalene. The UV spectrum of an ethanolic solution of an ethylene observed at 375, well above the principal absorption bands of naphthalene, and therefore to estimate anthracene, a standard solution of anthracene naphthalene is prepared and its observance measured at 375 nm by the application of Beer-Lambert law. The concentration of pure anthracene is anthracene naphthalene mixture can be calculated. Determination of strength of hydrogen bonding. Polar protic solvents such as H2O, C2, H5OH, CH3OH, etc. are known to form H bonds with the n electrons of carbonyl oxygen. This lowers the energy of the n electrons in the ground state by an amount equal to the strength of the H bond. Depending upon the strength, the n pi star transition of carbonyl compounds is shifted towards shorter wavelength. Thus, by measuring the wavelength max of carbonyl compound in a non-polar and polar protic solvent, the strength of the H can be determined. For example, n pi star transition of acetone in hexane non-polar solvent occurs at 279 nm, but in H2O it occurs at 264. This isochromic shift of 279 to 264.5 corresponds to an energy of 5. Thus, the strength of the H bond between H2O and acetone is which it is excellent agreement with known strength of H bonds. Identification of geometrical isomers. UV spectroscopy can be used to distinguish between a pair of geometrical isomers. In general, trans compounds observed at longer wavelengths with higher extinction coefficient than the corresponding cis isomers, for example. The reason being that in transtebene, the two phenyl groups are on the opposite side of the double bond. As a result, there is no steric hindrance, and hence the ethylenic double bond and the pi bonds of the benzene rings are coplanar. Consequently, more effective pi orbital overlap occurs. As a result, energy gap between HOMO and LUMO decreases, and hence pi star transition of trans isomers occurs at longer wavelength. Hence, the trans isomer observes at a longer wavelength. On the other hand, in the cis isomers, there is some steric hindrance due to the presence of two phenyl groups on the same side of the double bond. Consequently, the pi system is not coplanar, and hence extent of the delocalization decreases. Therefore, the cis isomers observes at a shorter wavelength. Further, because of coplanarity of pi system, the length of the chromophore is much longer in trans-stilbene than in cis-stilbene. Therefore, trans-stilbene has much higher intensity. Similarly, trans-cinnamic acid absorbs at a longer wavelength with higher intensity than the corresponding cis-cinnamic acid or allocinamic acid. Study of ketonal tautomerism. Beta-diketones and beta-ketoesters are known to exist as tautomeric mixtures, and their UV spectra show absorption hands which are characteristic of both the keto and the enol forms. They show two absorption band, a strong pi and pi star absorption due to enol form, and a weak and pi star absorption due to keto group. For example, ethyl acetoacetate in ethanol shows a strong band at 245 due to enol form and a weak band at 275 nm due to the keto form. Unlike ethyl acetoacetate, which predominantly exists in keto form, in ethanol, acetyl acetone exists predominantly in the enol form. 84% shows a strong absorption at 273. The unusually high value of lambda max is probably due to chelation in the enol form. Determination of relative amounts of ketone and enol form and calculation of equilibrium constant. In general, in polar protic solvents such as H2O, C2, H5OH are keto form predominates due to stabilization by H bonding. On the other hand, in non-polar solvents such as hexane, H bonding is not possible. Hence, enol form predominates due to stabilization by intramolecular H bonding chelation as shown below. Thus, the percentage of phenol formed decreases as the polarity of the solvent increases, since the intensity of absorptions in UV spectra are functions of the concentrations of the observing species. Therefore, UV spectroscopy can be used to calculate the relative amount of the keto and the enol forms and the equilibrium constant. Detection of formation of charge transfer complexes. UV spectroscopy is quite useful in detecting the formation of charge transfer complexes as discussed below. Many electron-rich organic molecules such as aromatic hydrocarbons, phenols and aromatic amines are known to form charge transfer complexes with electron deficient molecules such as picric acid, tetracyanoethylene. During the formation of these complexes, electrons are transferred from the donor to the acceptor molecule. This results in production of two new molecular orbitals, and the transition between these new orbitals gives rise to a new absorption band. In fact, the appearance of this new additional absorption band is regarded as a criterion for the formation of a charge transfer complex. Perhaps the best known charge transfer complexes are the picrites of aromatic hydrocarbons, phenols and amines, majority of which are stable and hence can be isolated and crystallized and thus serve as derivatives of above classes of compounds. Charge transfer complexes which are not stable enough to be isolated can be characterized through their UV spectra. For example, when I2 is dissolved in benzene, it forms a brown charge transfer complex which absorbs strongly at 290 nm, while benzoic absorbs at 254 nm and I2 absorbs in the visible region at 500 nm. Similarly, when TCNE is added to a chloroform solution of aniline, a blue charge transfer complex is formed which observes strongly in the visible region at 610 nm, while aniline and TCNE observe at 280 nm and 300 nm respectively. Study of hindred rotation and conformational analysis. UV spectroscopy has been used to study hindred rotation in O substituted diphenyls and sterically hindred dienes are discussed below. Study of biphenyls. Biphenyl is not a planar molecule. The two rings are held at an angle of 45 degrees. If large groups are present at ortho positions, coplanarity is further reduced. As a result, extent of phi orbital overlap decreases and hence ortho substituted biphenyl observed at lower wavelength which reduce intensity. For example, biphenyl shows while 2-methyl biphenyl shows. Study of sterically hindered dienes. As stated above, deviation from coplanarity of double bonds will result in reduction of pi orbital overlap with the corresponding shift of lambda max to lower wavelength and reduce intensity. For example, 2,3 tertiary butyl 1,3-butadiene, in which there is little conjugation between the two double bonds due to the bulky tertiary butyl group, shows lambda max at a much lower wavelength as compared to 2,3-dimethyl 1,3-butadiene, which observes at 224 nm. Progress of a reaction. UV spectroscopy can be used to determine the progress of some reactions by measuring UV spectra on liquids withdrawn from the reaction mixture from time to time. For example, consider the reduction of a ketone to secondary alcohol. As the reaction proceeds, the characteristic n-pi star absorption band of the ketone will start disappearing since alcohols are transparent in the UV region. Therefore, the complete absence of the n-pi star absorption band due to the ketone shows its complete reduction to the corresponding alcohol.